In this second lesson, we will go a little more in deep with the Arduino programming. Before doing that, let's do a quick recap of the first lesson. During the first lesson, we have seen what a microcontroller is. This is a complete computing system which includes CPU, so central processing unit, memory, input-output pins, and development tools. Programming of Arduino platform is accomplished through the USB port. In order to develop the applications on Arduino, it's possible to utilize the Arduino IDE development tool. As we saw in the last video, Arduino is not the only microcontroller platform. We have several. For example, we have STM32 by ST. We have ESP32 by Espressif as well. Furthermore, I have been recently utilizing Arduino Amiga for my recent projects, but again, Arduino Amiga is not the only platform available under the Arduino offering. Let me now propose you a part of a previous video I have published, just to show you which are the possibilities, the features made available by Arduino and by microcontrollers in general. Let's wake up fully the amplifier now through the remote control. As you can see, the Arduino, the microcontroller, is performing some initial checks before giving green light to the amplifier. In this moment, the microcontroller was measuring the current flowing through each one of the power tubes, and only when the current gets higher than a certain amount, the microcontroller gives a green light to the amplifier. So in this moment, this was achieved. So now we have the FM tuner selected. Through the remote control, I can act on the volume control. You might see the volume knob moving. As you might remember, the volume potentiometer is a motorized one, so I can move it through the remote control. I can, of course, change the tuning. And again, increase the volume, of course. I'm just reducing the volume. Another position, another input, FM tuner mono. As you can see, the LED on the right is switched off now. This is useful in case of weak radio stations in order to increase the signal to noise ratio. So how can we accomplish the scenario we have just seen? Arduino microcontroller is programmed in order to receive data and to transmit data. The data received come from both analog and digital inputs we have seen in the last video. The microcontroller processes all these information coming from the different sources and provide digital signals as output. Those digital signals are utilized for the display, as you can see here, for acting on the remote volume control, for acting on the main power relays, for selecting the audio input, and so on. In the next sections, we will see in detail how this can be accomplished. Let's examine now the first application. I have programmed Arduino in order to real-time measure the current flowing through each one of the 4 power tubes. As you can see from the schematics, we have these 4 ohm resistors from the cathode of each one of the 4 power tubes to ground. The cathode of the power tubes are connected to analog pins of Arduino. So we have 4 connections going from the 4 power tubes to Arduino analog pins. The internal analog to digital converters, they are 10 bits analog to digital converters within Arduino, are used to real-time measure the voltage across the 4 ohm resistor, the cathode resistor you see here. In this way, Arduino can calculate the current flowing through each one of those cathode resistors. Arduino can calculate the instantaneous power in watt drawn by each one of the 4 power tubes. This is utilized at both startup and during the normal amplifier operation. During startup, consensus for the connection of the source to the amplifier is given only when the power drawn by each one of the 4 tubes is higher than a certain amount, which means only when the 4 tubes are sufficiently warm in order for them to operate. During operation, Arduino will disconnect the main power relay if the power drawn by any of the 4 power tubes is higher than a certain amount. As you can understand, this is a safety feature implemented through Arduino. And here you can see the code which I wrote in order to implement such a feature. This is a screenshot from the Arduino IDE, and here you can see the 4 lines, the 4 analog read, and through these lines I can read exactly the voltage I see at the cathode of each one of the 4 power tubes. Still speaking about analog signals, Arduino is utilized to measure the signal strength received by the FM tuner. Furthermore, Arduino is utilized to check if the received FM station is properly tuned. In order to accomplish that, I have 3 analog signals going out from the FM tuner to the Arduino analog pins. The first one of the mentioned 3 signals is the one coming out from the pin 13 of the audio demodulator integrated circuit. The voltage measured at this pin gives an idea about the received FM signal strength. The other 2 are those which Arduino can read from pins 10 and 7 of the same audio demodulator circuit. The voltage difference between the voltage read at pin 10 and voltage read at pin 7 is an indication of the correct tuning of the FM station. Those information are then shown in the 2 displays. We will see that later. In order to accomplish these 3 measurements, we still have 3 analog read commands. Again, we utilize additional 3 analog pins. You have seen previously 4 analog pins previously utilized for the reading of the current drawn by the 4 tubes. And now we have other 3 analog pins. So till now we have utilized 7 analog pins of Arduino. Furthermore, Arduino is utilized to process digital signals as well, of course. The first example is the digital signal coming out from the FM tuner's prescaler. This digital signal is utilized by Arduino in order to calculate the received frequency from the FM tuner. You see the deployed code. I'm utilizing the frequency count library. You see here that in order to come to the received number, so the received frequency, and in order from that to get the received signal frequency, Arduino needs to do some math. First of all, Arduino needs to multiply the frequency received by 256 because, as you might remember from my last video, the prescaler deployed within the FM tuner divides the local oscillator frequency by 256. So again, in order to have the final received frequency in megahertz, I need to multiply the frequency of the signal I receive from the prescaler by 256. Furthermore, I need to subtract 10.7 megahertz because, again, as you might remember, the signal received by the prescaler is captured at the local oscillator. As you remember, the local oscillator frequency is 10.7 megahertz lower or higher, depends, than the received signal frequency. Also, in this screenshot, you still see analog grid commands. We have seen before, these analog grid are used to measure the received signal strength, we have seen before, and the status of the FM station, if tuned or not. The received information we have seen till now, coming from analog sources or digital sources, are utilized to feed the two OLED displays. Those two displays are connected to the Arduino I2C outputs. And in order to implement two displays other than one, I had to solve an issue. The issue is that I couldn't manually change the address, the I2C address of each one of the two displays. So both displays have the same address. For this reason, I had to implement a multiplexer. Here you can see the multiplexer card. It's deployed around the TCA9548A integrated circuit. This card is connected to the I2C Arduino outputs from one side. On the other side, the card is connected to both OLED displays. So this card makes two I2C outputs available for the two OLED displays. The card makes other two connections available, but in my case I will not utilize them. And here you can see the deployed code. As you can see here, I have to send information to each one of the two displays separately. Arduino microcontroller has a very interesting feature, like the majority of the computing system, which is the interrupts. I can configure Arduino in order to accept interrupts from outside the world. In my case, I can define some digital pins within Arduino, which will trigger interrupts. So any event, any signal coming from the predefined interrupt digital input pins will trigger an interrupt. So will stop Arduino from doing what it was doing before and triggers a separate code. So Arduino again will address the interrupt. This is very useful, and I have implemented interrupts for taking care of the remote control and the rotary encoder inputs. Any signal coming to Arduino from the remote control or the rotary encoder must be treated as quickly as possible, in fact. So this is the part of the deployed code. You can see I have configured 4 digital pins as input and as source of interrupt. The pins are the 18, 19, these are 2 digital pins. 18, 19 are utilized for the connection to the rotary encoder. If the user rotates the rotary encoder, then we have signals on the 18 and 19 digital pins. So as soon as the user rotates the rotary encoder, an interrupt is triggered. So Arduino stops doing whatever was doing before and goes to attend the interrupt routine, so goes to see what the user wants to do. The same for pin number 2. This is again a digital pin. If the encoder is pressed, so if the user presses the encoder, then I have a digital signal coming to Arduino through the pin number 2, and again an interrupt is triggered. The same for the remote control. This might not be so clear because I have utilized a library, but the infrared remote sensor is connected to the Arduino pin number 3, and again as soon as the user presses a button in the remote control, a digital signal is sent to pin number 3 of Arduino, thus triggering an interrupt. This screenshot gives me the opportunity just to quickly mention another command which I very often utilize, which is a digital write command. Through this command, you see here, I want to put the digital pin 13 in logic status low. This is utilized in order to switch off the internal Arduino LED for sake of energy saving.